So today we're going to define entropy and to look at entropy as a measure of a dispersal of energy. It's been defined in a lot of ways as kind of like the randomness of a situation. I actually prefer this definition a little bit more. And then we're going to describe the factors that influence the sign of delta S, which is our entropy for a chemical reaction. Okay, so walking out here today, you're going to compare the relative entropy of two different systems, such as a solid versus a gas. And then if I give you a chemical equation, which is going to include states of matter, you're going to predict the sign of the entropy change. All right, so when we think about why chemical reactions happen, we want to think about getting to a lower potential energy state, right? Like we are unstable, we're sitting up high on the shelf, on the cliff, and we're ready to fall off, right? And that's kind of what these chemical bonds are like. They're in a more or less stable position. If they're more stable, they're usually, lower on the cliff analogy. And if they are less stable, they're going to be higher on that cliff analogy. And so we want to think of going from high potential energy, where you have a lot of energy stored in the bonds, to low potential energy, where you have less energy stored in the bonds. And so when this is what happens, when you go from high to low potential energy, you're going to favor an exothermic reaction. Okay, so if you think about what's happening here in this match head that's burning, you've got a situation where that match is releasing energy. And when it releases energy, that means that energy is being dispersed. Okay. And so now when we have a match that's here, that energy has burned up and the match is burned up and the energy has dispersed and gone into places in the surroundings. And so we went from high energy here to lower potential energy here. But we also were doing a localization energy to a dispersed energy, right? So when you're thinking about that match, it's kind of an organized set of criteria that you can think of. Like all of these little molecules are in their little places. And once you burn them, then that energy gets dispersed. And so if you think about these little pictures down here, we have our solid that's turning into a liquid that's turning into a gas, okay? And you'll notice that the particles of the solid are all organized, and then they become a little bit more spread out, and then they become even more spread out. And this is the idea of dispersal of energy. Entropy is that dispersal of energy, okay? And so two driving forces that are making reactions happen, I'm either going to be going from the high potential energy to the low, or I'm going from the more organized to the more dispersed. Okay. So when we think about the tendencies for our exothermic reactions, most of our reactions that we know of are exothermic. And why? Because we're all tending toward having the universe cool down, right? So the energy in the universe is basically dispersing, and eventually we'll reach heat death, right? So we're proceeding toward a lower energy state, but it becomes more stable. And the exception to that, you can have reactions that are actually going to be endothermic naturally. Okay, in other words, we do this reaction and suddenly it feels cold. Like you can think of, mixing certain things together, and you're like, oh, why does this feel cold? An ice pack. Why does that ice pack feel cold after I strike it? Right? Well, because there are some things that are going to happen spontaneously, which are going to be allowing for something to take place that isn't exothermic. And that has to do with something that we're going to talk about now, the entropy. And so your enthalpy change alone is not the sole driver. You've got some things that are actually going to rise up. Okay, they're going to store energy in their bonds in a natural way. Okay, something other than enthalpy can determine spontaneity of reactions. So we are going to talk about how entropy ties into that. Kind of see here with our diagrams that we've got, this is the natural order of kind of falling down, right? higher energy to lower energy, but we can spontaneously do this other process. And we'll talk about when and why. And you already know some examples. We're just going to see what these are. All right, so if we think about melting, melting is an endothermic process that is natural at room temperature, right, for water. And so if we think about melting, melting is spontaneously taking place with our solid water at room temperature. Energy is being transferred from the warm air around, right, that surrounding air, and it's being transferred into the ice. And so this is becoming less organized. If you think about it, that ice crystal is pretty organized, and it's going to become less organized. It's going to have its energy more dispersed, right? And so if we think about our delta S, remember that's entropy, our delta S is going to be greater than 0 as we go from ice to liquid water. The localized arrangement is going to turn into a dispersed arrangement. Okay, so systems that can go from one state to another without an enthalpy change do so by increasing their entropy. Okay, so if you have something that is automatically endothermic, then there's got to be an entropy increase taking place in that. Okay, questions on that? All right, so if we look at our water going from solid to liquid to gas, right? If we're starting out with our entropy idea, our solid is very localized energy. Our liquid is becoming more dispersed, and our gas is even more dispersed. So you can see that the entropy, this should be an S here, I apologize for that. Our entropy of our solid is less than the entropy of the liquid, and the entropy of the liquid is less than the entropy of the gas, okay? And then if we look at our example for our melting ice, if we think about the water as a solid versus the water as a liquid, our entropy is going to be increasing as we turn from a solid to a liquid, okay? High entropy for a liquid, low entropy for a solid. Questions on that? Okay. So if I think about the entropy being the measure of dispersal of energy in a system, then I can make some conclusions here that if my localized energy increases, then my entropy must be decreasing. If my dispersed energy is increasing, then my entropy is going to be increasing. Notice that we're not using the same word here. One is localizing the energy and one is dispersing the energy. And so that's why both arrows can be pointed up in this case. We're not exactly using the same word for this relationship. And so if our change from initial to final results is an increase in energy dispersal, our entropy value is going to be greater than 0. For any substance, the solid state is less dispersed than the liquid state, and the liquid state is less dispersed than the gas state. Okay? Now, I don't really like this idea that we have here that's kind of displayed by this comic of entropy. And it was what I learned when I was going through school. Like entropy is like the chaos of a system. And so if you have less order, you're going to be, more, you're going to have higher entropy. But one of the reasons that I don't like an arrangement like this is because, if you think about all the objects that are in this room, these objects are not really dispersing their energy any more than when those objects are organized, right? The organized room versus the room that is disorganized, they still have the same number of objects in the room. Those objects aren't really dispersing their energy in any way. And so while it's kind of an interesting mental image that we can use, it's not really a very good scientific analogy because there's not really any movement of the particles out from some sort of localized area. Okay, so it's not really dispersing the energy. So I don't really like that concept as well as what we're talking about now. So when we talk about our entropy, we are going to be measuring our entropy in the units of joules per mole Kelvin. And we'll be pulling some of these values from tables. And when we talk about entropy changes, an increase in entropy will be a positive delta S, a decrease in entropy will be a negative delta S. Okay. So now we have a delta H that we've learned, and that's enthalpy, and we have a delta S now, which is entropy. And we're going to be tying these in a future lecture to something called Gibbs free energy, which is going to be a G that we're going to use. Okay, so joules per mole Kelvin. So let's look at some examples, and I want you to try to see why it is that we might have some of these values that we have for entropy with these examples. Let's look at the first one. These are standard entropy changes for some reactions, things that we've measured. Okay, you notice we have calcium carbonate as a solid reacting with hydronium ion, that's an acid, right? Whichever acid we might have in that case. And it's going to form calcium ions plus carbon dioxide plus water. Okay, it says that the entropy change is 138, meaning that it has become what? I'm going to call on indium. Yeah, so why do you think this entropy change is giving us a positive value? Why is our entropy increased here?
Just because it's more dispersed.
Okay, good. Tell me about more dispersal here with the equation.
It's because it's... I'm not sure. Is it because it's producing more than, like... I'm trying to think of the word. I can't remember what the word it is. But it has three things.
Yes, three things, three particles, right? Yeah. So we can have it's actually like we go from 3 particles over here, right? Calcium is 1 and then hydronium is 2. And suddenly we have 3 with our water plus the carbon dioxide plus some calcium. So we've kind of actually gone to 5 particles, right? So we're kind of dispersing our particles out to greater and greater places. Yeah, absolutely. So that's kind of the idea here, is that we have a positive entropy because we're going to disperse that value. And we can see that in the next one, we have sodium chloride, and it's turning into 2 different particles. So we're dispersing that. So it's going to have a positive entropy. Now, this one is a little interesting because it says we have 2 particles here, but we still end up having 2 particles here. And our entropy is still positive, which means we are still dispersing the energy to some degree, even though we have 2 particles in both situations. Now, what exactly is happening here? Well, we might have to look at some various different factors to figure out why. But in this case, we can at least experimentally see that we are dispersing that energy. Might have something to do with the overall masses, the speeds of the particles, things like that. If we look here, we have CH4 plus 2O2. We have the same number of particles over here, right? So we had 3 particles on both sides, and yet it's a little bit negative. We do have gases all the way around. And so again, why is it a little bit negative? Might have to be experimentally figured out. But now we get to something that's middle spots are kind of a little bit iffy, but now we get something that's a little bit more obvious. We go from 3 particles to 2 particles. So we're becoming more localized, right? And we also go from a gas to a solid. And so that's definitely going to be a decrease in entropy. So we're at negative 181. And here we have 2 particles as a gas compared to 1 particle as a gas. And so we're at negative 176. So our entropy is decreasing because we're localizing our entropy. Okay? We're localizing our particles, basically. All right. Questions on that? You can see some examples. A little bit fuzzy in the middle spaces, right, where we might not know exactly what's happening in there. But the ends make it pretty obvious as to why that's happening. All right. So I want you to predict the sign of the entropy change. Will your delta S be positive or negative for these 4 examples? I'm going to let you have a turn and talk and discuss these questions, and then we'll call on you.
Does that matter?
I think it's going to. I mean, it's going to be Earth.
It's going from 2
So it's
one.
Okay.
it's the gas.
Oh yeah.
Solids and gas.
And
That's
C,
the last
I think it's negative. And then negative.
one. Gas has a higher
You're saying it's positive?
and so it's on the gas is it's higher. And then solid and gas is solid.
All right. Looks like we have some answers that you guys have worked out. Let's see if we can come up with the correct answers. For A, bromine, what do you think? Okay, bromine is saying this is going to be positive. Why are you saying it's going to be positive, bromine? From a singular particle to two different particles. Yeah, we've got solid and also changing into a gas, right? Which is definitely a more dispersed form. So positive entropy. Great job, bromine. Let's go with calcium. Because negative, she says? Yeah, being more localized, becoming a solid, and a single particle from gaseous particles, which are two. Excellent job. Way to go. Right. Let's go with tellurium. Okay, saying positive. Why? Good, it's because it's becoming more dispersed. We have these multiple particles now. And also we went from a solid and then we have gases now as well, right? Great job. Okay, and now we have our last one going to iodine. Negative because we have a gas here and again, solid and only one particle there. Great job. You guys are nailing it. That is exactly right for each of those. Congratulations. All right, our catalyst. Let's go ahead and start with figuring out our formation equation. It's going to go to calcium. What you got? I'll just write down what you say. Okay. Okay. Good. So, what about our states of matter? C3 is okay. Now, one thing about the C3 that I've got a little bit of a problem with is that there is no Brinkelhoff C3 kind of situation, is there? So we're really not supposed to do a C3, even though we've got three C's. 3C, yeah, good. Okay, so you said that was a solid, and then our gas for oxygen, right? And then what's this last one? Yeah, it's a gas as well, right? So we can do those states of matter. Good job. All right, then we are wanting to take these two equations and use those to come up with our answer, which is that, right? That's our answer. So how am I going to do that? All right, multiply a second equation by 2. And then what are we going to do over here? Good. We multiply our enthalpy by 2 as well. Now, tell me a little bit more about this. Why does multiplying by 2 on the second equation get us to get our answer?
You can cancel out the CO.
Yeah. That CO now can cancel with that CO, right? And then what about what happens to our oxygen and our carbon?
You can add the carbons to get 3C, and then the oxygen turns into just O2.
Good. Our 2 carbon plus our 1 carbon here gives us our 3 carbons that we're looking for. And this becomes a 1, which is what we're looking for up here as well. Good job. Okay, so our final answer for this rubidium is going to be, how about, we'll go, since rubidium is not here, we'll go to antimony. Didn't quite get it. All right, how about strontium? Didn't go. Okay, what about tin? Oh, not here, tin. All right, what about iodine? Is iodine not here either? Oh, we'll get there eventually. Germanium! Okay, a negative 93.7 kilojoules. All right, good job. We take that to 3 sig figs because we have to get to the 10th place. That's what they have in common. All right, did anybody have any questions on that? Where, for those of you guys that missed that, questions as to why? What was going on? Not sure. Where did you get stopped?
So I just didn't see that you can multiply the bottom equation by 2 to cancel it out.
Okay, so you were trying to figure out how you could get them to cancel, but you just didn't see what was happening there. Okay, all right, but now you see it? Okay. All right, let's continue on then. We are going to talk about Gibbs free energy today. And we want to understand what Gibbs free energy is and talk about the factors that influence the sign and magnitude of our delta G. And then we're going to talk about what's meant by spontaneity of a chemical reaction, and we're going to relate that to our delta G. So walking out of here today, you should be able to describe Gibbs free energy as a combined enthalpy-entropy function. And when I say function, we're talking about a formula. It's going to be a mathematical formula. We're going to explain how Gibbs free energy changes in natural processes. And then we're going to talk about the effect of those enthalpy and entropy changes on the Gibbs free energy change and explain how this sign of Gibbs free energy is going to tell us about the spontaneity of the reaction. So let's think about some spontaneous processes. You can see the skier here. One is going downhill, one is going uphill. It's pretty natural to go downhill if you're on some skis. It's going to be the kind of the natural flow of things. Not very natural to go uphill, right? It's going to require some sort of energy input if I'm going to go uphill like that. And that's kind of what we want to think about here. We want to think about other types of natural processes. Waterfalls going downhill. Lump of sugar dissolves in a hot cup of coffee. Ice is freezing below 0 Celsius and melting above 0 Celsius. Heat is going from hotter objects or objects with more higher temperature to objects of lower temperature, right? Iron is going to slowly rust over time if it's in the presence of oxygen and water. Remember that these spontaneous processes could be fast or they could be slow. Iron is not going to rust very quickly, right? It's going to be a slow process, but it's still spontaneous. It's happening naturally. And so we want to think about processes that are happening naturally, and we want to think about why. And then we want to think about what processes don't happen naturally, okay? And we want to start understanding why some of these things happen with regards to an equation called Gibbs free energy equation. So let's kind of break down those two driving forces that we learned about in our previous slides. We learned that there was this enthalpy, that when things are exothermic, right, that you're trying to go from a place of higher potential energy to a place of lower potential energy, right? So you're going to become less, you're going to lose the energy that was stored in your bonds. You're going to become more stable when that happens. That's one of the natural processes that happens in chemistry. Then there was the other process we learned about. We learned that if you are going to become more disordered, that is also a natural process, right? That if you're going to disperse your energy, that process is also natural. So those two things help drive all the reactions. And we want to kind of describe 4 different types of reactions here. So we're going to look at 4 different scenarios. And we want to try to describe what each of these things means and what kind of examples we might have for each of these. So in this first example, I've got my delta H as positive, meaning that it is endothermic or exothermic? Endothermic, good. Why? Because remember that negative sign is exothermic, right? So positive is endothermic, and it says that it's getting plus on the entropy, which means that my energy is becoming more dispersed, right? And so I've got a situation where I have endothermic, but more dispersed. Okay, I want you to think about kind of situations that might be like. And the next one, I have something that's exothermic, but it's becoming more localized. So it's giving off energy, but it's becoming more structured, more ordered when that happens. In reaction 3, I have got something that is endothermic, but it's becoming more localized. And in reaction 4, I've got something that's exothermic, but it's becoming more dispersed. Okay? Now, these first 2 reactions, okay, we want to talk about. how could you determine whether or not reactions 1 and 2 are spontaneous? So some of these reactions up here must be spontaneous, or maybe 1, and some must be non-spontaneous. And then 2 of them may or may not be spontaneous, which I think you can probably figure 1 and 2 are the ones that may or may not be spontaneous. So you're going to do a little turn and talk right now, and you're going to try to figure out what criteria might we be looking at to figure out whether or not something may or may not be spontaneous. So in reactions 1 and 2, think about those scenarios. What makes them either spontaneous or non-spontaneous? Go ahead and do a turn and talk.
You gain energy, but you get more dispersed.
I want to say the exact same thing.
And
You gain more energy.
if you lose energy, its strength would also be spontaneous.
It occurs naturally.
Like the water.
And like based off it, if it's like a
Yeah, I get what.
The what?
I feel like the first two
I do.
there's like if you're adding energy to like ice, it becomes more dispersed. So then like they're just naturally
Are we right?
Yeah.
At what particular situation? Adding energy at ice, it's becoming more dispersed, but is there a particular time then that happens? Well, that's called melting, but when does melting happen?
When you add heat.
Not always. If I go in my refrigerator, if I go in my freezer and I get my ice cube out and I start adding heat to it, doesn't mean it melts. When does that happen?
It's a natural occurrence. Well,
When does it become natural? Because it can be spontaneous or non-spontaneous. All right, you guys ready to give it a shot? All right, so let's look at reaction 1. You've got something that is endothermic, so it's absorbing energy and is becoming more dispersed. Raise your hand if you have an example, an idea of what this might be. All right. Let's see what you have to say, Strontium.
Could it be ice melting?
Ice melting. Okay, I love this. This is exactly what we're looking for. Now, ice melting happens in a particular situation. When does ice melting take place?
Higher temperature?
Okay, I'm adding energy. And so at what temperature does ice melting take place?
At 1 atm it'd be 0 degrees Celsius.
0 degrees Celsius. So below 0 degrees Celsius, if I add heat, does it melt?
No.
No. Good answer. Yes, that's exactly right. If I'm below 0 degrees Celsius and I'm adding heat energy, I am going to be increasing the amount of heat that I'm putting into those bonds, but they're still not melting. They don't melt until we hit 0, right? And so that temperature is the thing that we want to look at when we say, how could you determine whether or not something is spontaneous or not? You want to look at the temperature, because temperature is the variable that will help decide if these two reactions are going to be spontaneous or not. Question or comment? Okay. All right. Did you guys figure out which one was always spontaneous and which one was not ever going to be spontaneous out of these two? Reactions 3 and 4? Anyone? All right. What do you think, my dear Selenium?
I think reaction 3 is not spontaneous
Because?
because it's endothermic.
Uh-huh. And
It's
becoming more what?
Close
Together, localized, right? Yeah. And so in a situation where I'm needing to absorb energy and also becoming more localized, that's not a situation that is going to be natural. That's like going uphill, right? And it is not going to happen without some sort of an input of energy. And so that means that reaction 4 is the one that is
spontaneous.
always spontaneous. Something that's going to be exothermic, giving off energy, and then also is becoming more dispersed, okay? So let's look at what a graph might look like if we were trying to chart the relationship between enthalpy and entropy. Now, Gibbs free energy is telling us that we can have a relationship between enthalpy and entropy if we're thinking about temperature as well. It says the overall potential energy of a reaction when both the enthalpy and the entropy are taken into account. So in this case, we're looking at a reaction that is giving off heat. And this graph over on the left, nitrogen and hydrogen are coming together to make ammonia, and it is becoming more stable, right? Because it has a little bit of energy that's given off. And so it's going from a higher potential energy state to a lower potential energy state. And Gibbs free energy is about the potential energy, right? And so this graph is showing us kind of how the relationship of this equation is working out over the course of a reaction. I am going to go from a higher potential energy state to a lower potential energy state. But the graph, you'll notice, kind of has two directions. You'll notice that over here we have an arrow going down on either side. Because what we want you to realize is that the reverse of the reaction can describe something just like the forward part of the reaction is describing something. So when I go from a place of higher potential energy here to lower potential energy here, then I'm giving off heat. So I've given off some energy in the space between those two parts, right? And I have done so by giving off enthalpy. Okay, so I have an enthalpic penalty, meaning I've given off energy in the process. Okay, if I were to go in the opposite direction, if I were to be going from here to here, then I was in a reverse reaction. It would mean that I'd have an entropic penalty, meaning that I'd have to go from a place of more dispersal to less dispersal, right? I'm going to have to go from the place where sorry, I should be saying that a little bit differently here. I've got 2 particles on this side as a gas, and over here I have 4 particles as a gas over there. And so I have paid for it with getting some entropy pulled out of it, right? Does that make sense? So you're either going to give up enthalpy or give up entropy or pay for it with one or the other. And so that's kind of what these graphs are trying to show you, is that you're either going to get some entropy or get some enthalpy, depending upon what direction that you're going to be moving. And if we go from right to left, then I'm going to have my entropy increasing. If I go from left to right, I'm going to have my enthalpy increasing. Okay? All right. So our Gibbs free energy is symbolized with the delta G, and its unit is kilojoules per mole. You'll notice that this one is in kilojoules. And what we learned about previously was that the enthalpy is in kilojoules, but the entropy is in joules. So when we do conversions, we got to make sure that we convert our joules to kilojoules. Our processes that are going to be spontaneous, the ones that are going to be the downhill skier going down the mountain, those are going to be negative delta G. So if you can get to a negative delta G, if you have Gibbs free energy that's negative, that means that this is a spontaneous reaction. Remember that just like enthalpy, we do this with experiments, and so we're measuring the changes that occur as you go from one thing to the next. Okay, so you've got enthalpic changes and you have Gibbs free energy changes that you're measuring. Okay, so here's our formula. Delta G, our Gibbs free energy, is equal to the enthalpy minus the temperature times the entropy. Okay, and again, we're noticing that we have deltas in front of all of these, right? So we've got these changes taking place. We're measuring the changes. So the change in Gibbs free energy is equal to the change in enthalpy minus the temperature times the change in entropy. Remember to convert from your joules to your kilojoules as you're doing these equations. This little guy is going to be given to you in joules. Make sure you convert it to kilojoules, okay? Your delta G being less than 0 means that you're spontaneous. Delta G greater than 0 is non-spontaneous, as written. But if you reverse the reaction, then it would be spontaneous, okay? And then our delta G being equal to 0 means that we're at equilibrium. So this is the place, for instance, let's think about ice. In that particular situation, when ice is melting at 0 degrees Celsius, you also have the water freezing at 0 degrees Celsius, right? You have both things taking place at the same time in equilibrium at the same rates. And so when your delta G is 0, that's when you're hit equilibrium and both processes are taking place at the same time. Any questions so far? Okay. So let's look at some examples in the real world. We talked about 3 and 4 already. Let's see how they connect to our formula, okay? So our formula, delta G is equal to delta H minus T delta S. Let's look at the situation that we talked about before with freezing. We said that with freezing, we were going to become more localized, right? So our entropy was negative. And we said that with freezing, we're giving off energy, right? And so we are exothermic. So both of these are negative. So what happens in a formula if both of these are negative? If my delta H is negative and my delta S is negative, then that means that whatever T is, this whole thing is going to be negative. And a negative times a negative is a positive, which means that depending upon what your T is, that's going to determine how big this is. And so this could be a big positive or a small positive, which means that we don't know whether or not this will end up being negative or if it'll be positive. And so this is one of the examples where temperature determines if this is going to be spontaneous. Okay? On this one, boiling is going to absorb energy, that's endothermic, and our process is going to be basically giving us more dispersed energy particles, so that's also positive. So if we plug those values in, if my delta H is positive, and then my delta S is positive, that means this is necessarily going to be negative, right? Because of the negative sign there. And so that means that depending upon how big this is and how big my temperature is, then this could either be positive or negative when we do the calculations. So the temperature, once again, is determining whether or not this is going to be positive or negative. Does that make sense?
Yeah.
Okay. Then if we look at decay of leaves, okay, this is one of my favorites. How many of you guys have gone and you jumped into an old pile of leaves, or you had to put them in a trash bag or something, and you reached your hand inside that pile of leaves and felt something? What did you feel?
Well, I really just felt the leaves and they were all crunchy. And
Okay.
It sucked.
Okay. Crunchy leaves. I'm looking for something else in this case, something. It's wet. And when they get wet, what else do you feel besides the wetness? Mold. You don't really feel mold necessarily. Maybe slimy, itchy. Warm. Yeah, that's what we're looking for here. That if you've ever reached your hand inside that wet pile of leaves, it's warmer on the inside than it is on the outside. Well, the reason for that is because that is an exothermic process. You are actually generating heat as those carbon-carbon bonds are breaking apart, just like burning, right? As they're breaking apart, they're going to be giving off some energy. And so you've got some heat that's being produced. And of course, is this becoming more or less dispersed? These leaves, are they particles being more localized or they're being dispersed? Dispersed. Leaves are falling apart, right? They're falling apart, they're getting more dispersed. And so if I have a greater entropy, then I have a situation that looks like that, right? Leaves are coming apart. Question?
Talking about the signs of delta H and delta S, but could T not be negative?
T cannot be negative. Why?
Well, I know, I was asking you.
Asking me. Okay, let's go back to our evidence that we have here. What do you see? What do you see?
Oh,
Can T be negative?
no.
Why?
Because you can't have a negative Kelvin.
Because you can't have a negative Kelvin. Exactly. So all of our temperatures in this process need to be in Kelvin. If they're not, if we try to keep it in Celsius, it's not going to work. We've got to convert to Kelvin. Yeah, good question. All right. So then we've got a negative for delta H And then we have a necessarily positive value here, which means this is a minus. And this is going to have to be minus because we have no matter what our temperature is, this is always going to be negative. So this is always going to be negative, which means this one is always going to be spontaneous. All right? If this is always negative, then this is the reaction that's always spontaneous. This is the natural order of things. Leaves decay. Okay? That's the natural process without energy being put into it. Leaves decay. Now, if we do the opposite part of we're building leaves, right? And then now we're making stuff from the air. We're taking these gases. These gases are all dispersed energy. We're pulling them into the plant and we are localizing them. We are trying to make this little guy turn into crystals, little crystals of sugar, carbon-carbon bonds, which means we're localizing our carbon dispersed stuff and putting it into a crystal. So this is a negative entropy. And of course, this is going to take energy from the sun, right? So this is a positive enthalpy. And so now we plug these values in. This is a positive. This is going to be a negative, and a negative times a negative is a positive. This is always going to be positive, which means this is always going to be non-spontaneous. Okay? Does that make sense? Questions on these processes? We can see it in terms of a formula, and it's kind of neat to be able to look at what's happening in nature, decays of leaves and photosynthesis and freezing and boiling, and look and see that these processes can be described with mathematics, and through thermochemistry, we have these energy values that we can actually assign to things that are actually happening in the physical world around us. And I just think that's pretty beautiful. Okay, let's see what we can do in terms of a problem. This is what a problem like this might look like. First of all, we've got to process this solid water turning to liquid water, right? And so we know that this is ice that's melting and it's got to absorb some energy. So we know we're dealing with an endothermic process. We know that the solid was more localized and the water, as it melts and kind of spreads out all over the place, is dispersing the energy. So we have a positive delta S. So we can kind of get an idea of what it is, but we know that this is now a plus delta H and a plus delta S. So this is one of the things that is determined by our what? Temperature. Okay? And so what we're going to do is we're going to say, all right, let's plug in our value that we know for delta H. Our enthalpy of melting is 6.03 kilojoules per mole. Our entropy, we would have to look this up in the back of a book, is 22.1 joules per mole Kelvin. So we need to convert that to kilojoules, right? So we can see that being converted to kilojoules down here. And then we plug it in. So here's our 6.03 kilojoules per mole minus our temperature. Ooh, we've converted that to Kelvin because it's got to be in Kelvin. So we took minus 10 because that's the question. At minus 10, is this a spontaneous situation? And we say, okay, well, let's multiply those together, get our answer, 0.22 kilojoules per mole. That's a positive value. Remember, spontaneous delta G is negative. This is positive delta G, so we say no, this is not spontaneous. But look at this. This is kind of cool. The reverse, remember, is spontaneous. So think about it. Negative 10. Does ice melt at negative 10? No. However, is the reverse true? Does ice freeze at negative 10? Yes. And so at negative 10, you have a spontaneous situation of ice freezing, but not of ice melting, right? And so that's why the temperature, in this case, that negative 10, is determining whether or not this is spontaneous or not. And the fact that you can look at the mathematics of this and see if ice is melting, not just because of a temperature, but because of what happens with energy and how the world works with regard to Gibbs free energy, you got to admit, that's pretty beautiful. Right? That's pretty cool. All right, let's see if you can do it on your own, right? Let's see if you can take this equation and tell me if this is spontaneous at this temperature. Okay, we have a chemical reaction at a particular temperature. Is this spontaneous or not? So let's look at our answer.
Oh wow.
Okay. And again, we were asking about what was happening to our temperature. This temperature here could be 278.2. But when you multiply your 278.2 times your negative 0.135, the answer here is going to have 3 sig figs, right? Because when you multiply, your answers are going to be to 3 sig figs because it's the least that you have to get it in common. And so you have a 3 sig fig value and a 3 sig fig value that you're subtracting. And so then you would still try to make sure you see what's in common. So